goal is to finish discussion of lasers and get started on the aspects of material science. So let me just switch this off first. Okay, so and I'll make some announcements hopefully in the end of the class if about the assignment and midterm. The reason I have not posted it, a couple of reasons, but one of them is because I am at least one or two of the problems in the assignment will be kind of your midterm exam rather than having a separate exam. So it'll be take home with the assignments. Okay, so we were discussing about optical properties, primarily the aspect of kind of leading towards LEDs and lasers. But one of the major points we were discussing is the most of the these whether a material, what conditions does a compound semiconductor material emit light, and how can you make it emit light in an incoherent fashion or spontaneous emission? That would be the situation for LEDs, or in a very coherent fashion, which is the situation for lasers, right? So what we kind of ended up, the place where we ended up in the last class was kind of saw where the microscopic origins of the absorption coefficient of actually in general any material, but specifically we were looking at semiconductors with a conduction band and a valence band with well-defined effective masses, right? And the end result of this exercise was actually rather simple in the sense that you can write down the net absorption coefficient as a function of the photon energy, right, under any equilibrium conditions, meaning non-equilibrium conditions or equilibrium conditions, as an equilibrium absorption coefficient times a measure of how far are things from equilibrium, right? So this was kind of the central relation. I think it was in the in this particular slide. And what are the details of this expression? The equilibrium absorption coefficient, let me write that down just so that we are clear what are the parameters that go into it. So it is some coefficient times reduced this optical density of states, which we can write like this. So if you have found the conduction band density of states or the valence band density of states, this thing kind of combines the two, right? And for example, for three-dimensional semiconductors, if you know the spin degeneracy, value degeneracy, right, and then essentially you can imagine you're just writing your conduction band effective mass, but you've got to replace the effective mass by the reduced effective mass. We saw that for both electrons and holes. So 1 over conduction band effective mass plus 1 over valence band effective mass is this 1 over m star reduced mass, right? Times a square root of the photon energy minus Eg. So that's your equilibrium absorption coefficient for 3 dimensions. Right? So I think for in 2 dimensions it will be m star by pi h bar square times unit step function, and then for 1 dimension it will be 1 over square root and that sort of thing, right? So okay, so that's the reduced density states, but in and in front of it there is another coefficient that comes from all this photon counting that we did. How many photons are there in the incident light beam, right? That's we're just saying it's pointing vector basically the Poynting vector tells you the intensity of light that's incident or the power incident. So after all said and done, you get this additional coefficient labeled as C0, and that is your total alpha naught. And the C0 is dependent on, essentially it's written there, electron charge squared divided by the refractive index of the semiconductor. Right? The refractive index of the semiconductor times the speed of light times the dielectric constant or the permittivity of vacuum, free electron mass squared, not effective mass but the free electron mass squared times the frequency of the light that's incident. So that's kind of the entire so here the only material property that enters is the refractive index, and in a way because I think the speed of light is not 3 times 10 to the power 8 meters per second inside a material. It's slower, right, by the refraction. So wavelengths are shorter and such things. So that's why it enters here. So this enters as a macroscopic property, right? The refractive index here. And then there's free mass, electron square, and all that. It can be related to the fine structure constant and such things, but we don't need to get into much details here. But what we note is there is the frequency of light, or in other words, the energy of light in the denominator. This is sitting here. Okay, so when you kind of combine these quantities, what you get, let's just look at the magnitude of the absorption coefficient. So you will get of the order of 10 to the power 5 inverse centimeter, and I think there's a 2 or a 3 here. Let's call it roughly 2 times. And then I think you can see how all these parameters enter. If you have valley degeneracies and all, so they'll enter there. But as far as the mass goes, effective mass goes, it goes as 3/2 power for the 3D situation. So okay, it's here. So you can, it's been non-dimensionalized now. So h bar omega minus Eg is in electron volts. In EVs, let's say, all right, and effective mass is non-dimensionalized now to the power 3/2, and then so there's this extra term here, which is referred to as the oscillator strength, and this goes as, let me just write it in this way right now for simplicity, m naught over h bar omega. So this omega kind of comes from here. So it's an energy scale which is like momentum squared by mass, characteristic of the semiconductor, and this is called the momentum matrix element between the conduction and valence band, interband momentum matrix element. And so the order of magnitude of this quantity is about like 10 eV or so, roughly 10 eV. And this is again the photon energy in a few electron volts, depending upon what is your energy incident. Okay, so that's typically the oscillator strength. And just a general trend of these things, of this whole thing, if you keep, everything is, let's say, of the order. So this will be slightly larger than 1, and this will be slightly smaller than 1, as you can see, if smaller effective masses and such. So given everything, things are of the order of 10 to the 5 inverse centimeter. So that's kind of the whole thing here. And that's why if your absorption coefficient is 10 to the 5 inverse centimeter, then so 10 to the power minus 7 centimeters is 1 nanometer. So you can see you will take about 100 nanometers to drop the intensity of light by a factor of E, and then again. And so that's the typical absorption length, right? 1 over that is the absorption length of the order, right? And the other thing is, clearly, if you can increase the oscillator strength, you can absorb stronger. And the nice thing is, if you can absorb stronger, we'll see you can also emit stronger. So it's a reciprocal behavior. And then larger is the reduced mass. The larger is the this property. So higher density of states will allow for more light emission and more light absorption as well. So that's okay. There are some details on this slide. If you go to a quantum well instead of a bulk material, then essentially you have to take into account a couple of other factors: the angle at which the light is incident to the quantum well, and such things. But I don't want to get into those details in this class. So there, when you are really designing a quantum Hall laser, some of these parameters become somewhat important. I mean, essentially, most of these things, and this table, for example, tells you what is this momentum matrix element, and there's some cosine theta factors or sine theta factors in it. So, and that tells you the direction in which the light will come out, for example, or get absorbed. Okay, so what we'll do though is kind of, is that clear? I mean, that where all this came from, and what's the connection to the band structure and such things. Okay. Any questions? Okay. If not, so I want to now discuss this this aspect of it. So that was equilibrium absorption coefficient, and I'd obviously just about started discussing the non-equilibrium part, and so we will spend a little bit of time discussing that part of the story now. And I think you can also see from just one more point here that as you increase the photon energy much larger than the band gap, it absorbs more and more, right? So you see that if you're just slightly above the band gap and your absorption coefficient is 10 to the 5, if you are, I don't know, 4 times the band gap, it's twice. So it gets absorbed in an even thinner region, right? So for example, if you take say 2 electron volt band gap semiconductor and you shine 2.2 eV photons, then it may get absorbed in 100 nanometers. But if you shine 4 eV photons, it will get absorbed in maybe 50 or 30 nanometers. So it gets thinner. Right? So, makes sense? Okay, so now we are interested a little bit more in the inverse process of absorption, which is the emission process. And for emission, there are essentially two kinds. Just looking at the band structure picture, I think you can readily see that you can have various kinds of situations. You can have a situation where you have put an electron here and a hole here, empty state, and it just recombines with the electron recombines with this hole and emits a photon, right? So that would be called a spontaneous emission. Electron recombine with the hole, and you get light out, and so it recombined spontaneously. There is no nothing kind of tweaking it to do that. Right? And then obviously you can have the other situation, which is where you again have created similarly an electron and a hole, and by now I think we hopefully we understand that because the photon has a very long wavelength and its momentum, which is basically Planck's constant by wavelength, right, by de Broglie relation. Because the wavelength is very long, the momentum is very small, so we have vertical transitions, right? Is that clear at least? Whereas electron wavelengths are angstroms, right? I mean, or these are lattice constants, sort of. Therefore, they have much higher momentum than the photons. So, because of the mismatch, they. Okay, so this is that's why we have only vertical transitions. Okay, so the other kind of transition would be it recombines, but it's kind of helped by a photon that was already incident. And then what goes out is 2 of these photons now, right? So it can be like that, and so that would be called a spontaneous process, and this would be called a stimulated emission. Right? Right? I mean, this part is clear. So if you already have a photon, then that is stimulating this process to happen. And just as from the fundamental particles, so the photons are very unlike electrons, right? Photons are called bosons, whereas electrons are fermions. And from the most basic quantum mechanical properties, because you can put as many photons as you want or as many bosons as you want in one state. Okay. Whereas electrons have a problem because of the exclusion principle, right? So you cannot put more than one in one state, right? You can put spin up and spin down, but not more than one. But bosons have this property that the probability basically, if you have a certain number of photons or a certain number of bosons, it enhances the probability of creating even more bosons. So the probability is enhanced because so essentially the probability. Let me just write it this way: probability of putting, say, a photon, number of photons in a certain mode Q. This is a very rough argument right now. Okay, is actually equal to 1 plus the number of photons that are already there. This is the relationship for bosons in general. Number of bosons in any mode Q. And this comes from from the statistics. These things follow. For example, okay. So if you create, if you want to transition from, I don't want to get into that. Basically, you get like a square root of this as a coefficient, and then your probability is the square of this. So what does it mean? That if I have no photons at all, 0, I still have a probability of emission. And that's spontaneous emission. Right? But if I have some, then it's enhanced. The probability of creating more photons is enhanced. Okay, so that's the property of bosons in general, and specifically light or photons here. On the other hand, if you have, this is just an aside, not very important right now, but so for fermions, this same probability, kind of hand wavy way, but actually not hand wavy way. It is just this, where, so that's how it looks for fermions, for electrons or protons. So if you because of Pauli exclusion principle, you can't have NQ can only be 0 or 1, right? So if it is already 0, you can put 1 in, right? But if it's already 1, you can't do any more. The probability is 0, putting 1 more. So that's kind of a way to look at it. Okay, so this is just an aside at this point. Okay, so when we have this process dominate in our compound semiconductor device, when this term dominates, we have a LED. But when this term dominates, you have a laser. So that's the key. That's the differentiator. Which one dominates? Okay, so and in a laser, so just as a looking at what do you mean by Q, the end game of this would be, you will have your LED device, which is your quantum wells, and you have your P and N, and these are quantum wells, and you inject holes and electrons into the region, and then out comes light, right? So h bar omega, right? But in a LED, the light is going to come out in various directions, okay? And when it emits, the spectrum over energy is going to look, let's say this is what you have designed of the quantum well interband transition energies. The spectrum will look something like this. So there will be some broadening. Not just in energy. So this is the intensity of output, of photons. Not just in energy. So this is obviously, okay, it's broadened in energy. With a peak at some point. And in LEDs, typically, if you're looking at, as you might imagine, if you're looking for some applications, the broadening is actually useful for some applications. So because you can it can have many applications. You can design it to have multiple things, multiple peaks and all that. But the main point here is it's coming out as it's not quite all the same energy. And the second thing is it's also coming out with different directions of the so the photon energies and then the direction. Right? Photon is a as a direction for propagation. So, for example, kx, ky, and k. Let's call it q is the photon wave vector, which is 2 pi by lambda along the y direction. Let's say. So I hope this is clear what I'm writing here. Basically, mod of q is 2 pi over the wavelength, and the wavelength is 1.24 micron over the energy of the photon in eV, right? This part we know, right? The wavelength and the energy are related through that, right? So that's the magnitude, but the direction. So what happens now is if the LED is sitting in vacuum, let's say, or in air, then the light can go out, right, in any direction, depending upon. Actually, let me put it this way: the direction in which the light is emitted that's where all these thetas come in. These thetas tell you what direction are they going in. Okay, so. And generally, what will happen is go out as a cone. Some cone, but then it will try to get out and then get reflected, and then you have to do some stuff here to get it out. What people typically do in industry is the surface is roughened, intentionally roughen it, so that there's always a path for it to get out. There's some so you're not below the total internal reflection, so you can get out. Okay. Anyway, so what I'm trying to get to is if you are emitting into vacuum and into air. Then basically you can imagine air as a very large box, and again for the photons that will fit into the air, just like electrons had to fit into the crystal. Now the photon that has emitted has to also fit into wherever it's going. The photon has a wavelength; it's much longer than the crystal, right? And the size it's coming out. But if it's going out into vacuum, then essentially what you have is all these points in the k space or the q space of the photon, into which you are emitting. For example, if a photon is going, along the this direction, let's call it the y direction. If the photon is going exactly along the y direction, so it will have, a certain q that corresponds to this energy through this relation, and a magnitude somewhere there. Make sense? Okay. But since it can go in various directions, I think you can already see what you'll get here is kind of a many modes that will occupy. Maybe this one will be occupied, maybe a little, this one will be occupied, and this one. So when you combine these modes, sum them up, that's what you get. Just different angles, and different energies, right? Okay, so that's the meaning. So you're emitting into various modes, and why are you able to emit into various modes? Because the light is going into air or vacuum, and it's not getting reflected. There's nothing to confine it. Does that make sense? So you essentially, the main point is in an LED, you kind of fill up a certain number of modes like that. Is that clear? Or any questions? Okay, so now just like so for each mode of photons or light, you can have what you can call as a right circularly polarized or a left circularly polarized light. These are the polarizations of light, and the polarization is also determined by this matrix element here. That determines what's the polarization, is right circularized, left circularly polarized, and that goes back to the valence band and the conduction band profiles. So depending upon if this is S-like and this is PX plus IPY, then maybe it will be right polarized. If it's PX minus IPY, it will be left polarized, and so on. That's where it comes from. So, and that is, I think you realize it's the angular momentum in some sense, right? It's the helicity of light, right? So it has a, classically you can imagine if it's right polarized, it can actually rotate something, a dipole or something, because the electric field is kind of going this way, right? It has a certain torque in some sense, electrical torque, right? It can. So if you have, for example, a liquid crystal display, and you pass this light through it, it can turn the liquid crystals in a certain orientation. That's how actually LCDs work anyway. So, yeah. Okay. So that would be the LED picture, and what the reason I I'm describing this is, so how do you get to a laser, and what's the difference between a LED and a laser, right? So in a laser, what you do is you don't let light to go out in all directions. Right? So what you'll do is basically you'll put mirrors. I'm just putting it here for now. Actually, let's put it this way. Okay. So what you'll do here is let's say you're going to put it inside a light box or a mirror, conceptually at least, and then we'll see how you're going to actually do it. And this is a mirror, and because of the size of the mirror, now let's say this is Lx and Ly and Lz, or a box, for example, then not all modes are allowed anymore now. You see that? Only certain modes are allowed now. You select out certain number of modes. And the way you select out is you had the LED, and what you'll do is essentially, so a certain number of modes would be allowed based on the basically just the physical size of the box, right? And the wavelengths of light have to now fit. They have to be like that, or like that, or like that, and so on. They have to fit in that, right? And because of this, you have a certain, again, you get an integer number, basically the half wavelength times an integer along any direction, say along the x direction, must be equal to Lx, right? That's how it must be, right? So that will basically discretize what wavelengths you can get. And whenever you discretize what wavelengths you get, you discretize what energies you can get, right? So what you get now is a comb of energy. Basically, only these are allowed now, okay? Once you put it in the box. Is that clear? Only those. Basically, what I did was I write it in terms of energy, but I think you can easily convert it from the wavelength, right? I mean, that's not a problem. And only certain ones are allowed. And now you can see that even though the LED kind of wants to emit like this, now there is one wavelength, one particular mode where it will all go, because others are not allowed anymore. Right? Does it make sense? So that's the whole game. As you pump it, and essentially as it goes towards the laser, this this emission feature will start looking initially. Essentially, what will happen is it will kind of grow a little bit here, reduce here, then grow a little bit here, reduce here, and it will start looking like that. Actually, it will be higher. I'm just scaling it down. And finally, when you get into the laser mode, you will have basically just one peak here, so just one mode. Okay, so that's how you go from the LED to a laser. Essentially, the game is to have mirrors around it. And the mirrors really make this possible, because what's going on now is light is generated inside the quantum wells, and then it wants to get out, but then you kind of bring it back. So let's say light wants to get out here, but then you reflect and bring it back. And then you reflect again, bring it back. So you're continuously, basically you're stimulating the emission now. Right? So that's how you're increasing this NFQ now. So you typically do multiple passes before it gets out. Ideally what you'd like is one of them to be, it's never quite 100%, but you would like close to 100%, the other to be maybe 99.99 or something like that, reflectivity, and then the laser light really comes out from this side. So it's essentially a little bit of it is leaking out continuously. So that's conceptually how you make the laser. And this picture is really no different from how gas lasers were made for the first time. I mean, lasers were the predecessor was a maser, which was a microwave, microwave version instead of the optical version. That was the first real laser in some sense, and then for the and then the semiconductor lasers. The maser, then those gas lasers, right, using carbon dioxide or argon, or where you have these big. Basically, when you see, go to the optics lab and you see a big laser, what's in there? There's purified gas instead of a semiconductor, and then there are mirrors, right? And in a semiconductor, you are injecting electrons and holes. You are electrically, with basically just above the band gap of the semiconductor voltage, you can start kind of injecting enough current. In a gas laser, what you're doing is you're first exciting it with another light source. So the atoms are excited with another light source, which have a broad spectrum, and then it dumps all the energy to an atomic transition instead of a semiconducting transition. So these are atomic levels. Okay? So and then the light is emitted, but then what you do is make the light go back and forth again, put mirrors around it, and then one of them is where it comes. So that's a gas laser, for example. Okay, so so what is extremely important then in the laser? So the end result of this is in a laser as opposed to in a LED where you have a kind of a little bit of a cloud of regions where modes into which the light is emitted. In a laser, you will typically want only one. So all of the light goes into only one. Initially, when it's just about start lasing, what happens is okay, so you have a luminescence, electroluminescence like this, and then as I mentioned, you have multiple modes. So what will happen is you kind of start seeing the luminescence like do that. So and then once you cross the threshold of lasing, that's when you get only one peak. So what happens is this spectrum, or the width of the spectrum, really narrows. The width of this spectrum, as you measure the luminescence, it narrows. It goes into one. And initially, so in the process of going from a broad, spontaneous emission spectra to the, stimulated emission spectra with one peak, there's quite a bit of nonlinear dynamics and such things that go on. Essentially, what happens is this mode, the dominant mode, it gets into a very nonlinear regime. If it was a linear process, then every mode will have its equal share, so it just keeps going up like that, right? It doesn't change. But the moment this nonlinear aspect kicks in, then essentially this mode just sucks out all the energy from other modes and just dominates. So that's what happens in a real laser when you get lazy. So that part of it is a little more. So you saw people solve rate equations and all to see that process, but okay, some details there. So what is most critical then is, as the light passes through this semiconductor material where the light is being generated, and it's also the gain medium, meaning, this process where you have the stimulated emission where, 10 photons coming in and 11 going out because of bosonic nature of photons. This material, obviously, first things first, it must not absorb the light. It must, right? I mean, the absorption, so for this to happen, the absorption coefficient must be negative, as you can see right away, right? So only then you have gain, right? So this is, as a result, this media would be called the gain media, and you want the light to kind of pass through it multiple times. And so the competition is always between gain and loss. There will also be loss, right? Okay, so as the light goes through, just as again a sketch, this is your optical cavity from 0 to L, and let's say your light started out here because of a reflection on this mirror, and as we said, your intensity of light is going as e to the power minus alpha x, right? Where alpha is the absorption coefficient now. Let's write it this way. Right? That's how it's going. Intensity, absorption coefficient. Right? So now if alpha is negative, obviously it's going to grow, right? Intensity is going to grow. Right? It's going to grow, and that's what's gain, 10 photons, 15, 20, and so on. Right? But if there is loss, and the loss actually happens in parallel, then it kind of decays, and the question is, you have to fight both. I mean, so the loss would be non-radiative processes like OJ, like defect assisted, and all these other things. Same thing as LED. So you have to balance out these, and so right. Okay. So that kind of gives you, depending upon the reflectivity on one side of the mirror and reflectivity on the other side, you can write down an equation that will give you kind of a sweet spot for the length if you know your absorption coefficient and losses. So it will give you a kind of a nice spot. So that's in lasers course. Okay, but let's look at the absorption coefficient a little bit more now, because that's the gain is the critical element, right? So you can make your material as pure and all that, and then you'll be stuck with that. Now the game is to increase that, the absorption coefficient, so that you overcome the losses, right? Okay, so this term then, the non-equilibrium part is really the knob that you can turn and make your absorption coefficient higher or things like that. This is the knob you can turn, because this depends let's look at what this term is. Okay? Any questions here, by the way? I'm just maybe going through really fast, or it's also quite a bit qualitative at some point. But yeah. So what we want to now do is look at this knob that you have in an electrical injection process. This is fixed by the material, but this one is essentially. So again, the K naught is this square root of this quantity, and basically you are looking at a difference of Fermi functions. Okay, so it's a difference of Fermi functions of K naught minus Fc of K naught. So yeah, I mean I think I'll not write it down. You can plug in the values of Fermi function of the valence band, and then here's the Fermi function of the valence band. If this is the Fermi level of valence band, quasi-Fermi level, then the Fermi function F is 1 below that, and it goes to 0 above that. Right? It goes through half and goes to 0. Right? Similarly, Fermi function of the conduction band is 1 below the Fermi level of conduction band Fc, and then it goes to 0. So this whole thing, both these terms are between 1s and 0s. That's all. You're taking a difference of the two. It's a difference of two Fermi functions. And I think you can clearly see here that, let me sketch this out. So let's say this is f of c, this is f of v, all right? And the Fermi function of the valence band is going to do that, and the Fermi function of the conduction band is going to do that, right? Okay. This is 1, and that's 0, and that's 1, and all that, right? And what we're looking at is the difference, right? The difference, but which way? Let's plot that out, and that's the important parameter here. Essentially, what I'm going to plot now is this whole quantity then, here, right? So the difference is Fv minus Fc, right? Fv minus Fc. So this basically this function minus that function, right? So here is 0. That's 1. So this is actually negative in this window. So first of all, if you're down here, it's 1 minus 1. Right? So that's 0. Right? So there's nothing left. So you get a 0. And then the moment you get in here, you get basically this obviously dies, so it goes negative right now. Right? Am I doing it right? Fv, the Fermi function. This is f of v of sorry. Something like that, right? Is that clear? Yeah. Okay. So what you see is essentially it'll be kind of 1 somewhere middle of the gap and all that. But what is interesting about this point is you can, and this window. It's extremely critical that this window here, if your band gap is kind of like that, it does nothing to you. The band gap of the semiconductor is useless, right? I mean, nothing much happens. So the band gap has to, this window must be, basically the band gap of the semiconductor must be smaller than the window, and the Fc must be inside the conduction band, and Fv must be inside the valence band. Otherwise, even then, you are not doing anything very useful. So that's kind of a very important thing. And that's what this, once you mathematically take the difference, what you realize is let me just now sketch this. This is probably the most important figure in the discussion right now. So what I can sketch now is the photon energy, h bar omega, and first let's plot just alpha naught. So alpha naught is just the equilibrium absorption coefficient, and I think we already found it goes as C naught times some coefficients times square root of h bar omega minus Eg. For 3D. For 2D it will be steps. This is equilibrium absorption coefficient. Alpha 0 of h bar omega is proportional to that. Right? The equilibrium absorption coefficient. Now what we're doing is we're multiplying with the difference function, and now I'm going to plot it instead of this energy scale. I'm going to plot it what is even more important in a laser LED is the photon energy. It's not the band structure energy, but the photon energy, h bar omega. So let's plot it versus h bar omega. So what am I doing? I'm plotting this quantity now as a function of h bar omega. Where does h bar omega come into that? Well, it's sitting right there in the k0. You can put it in, just plug in, find the difference. What are you controlling? You are controlling, by electrical injection, two quantities. One is Fc, quasi-Fermi level of electrons, and Fv, quasi-Fermi level of holes. Those two things you are controlling. How are you controlling it? By the voltage you apply. So remember, you are in a p-n junction, and this is the active region of a p-n junction. If voltage applied is 0, your Fc and Fv are equal. There is no two Fermi levels. There's only one. This equilibrium, right? You apply a little voltage, and you split the quasi-Fermi levels. The conduction, if you apply forward bias, the conduction band goes upwards, and valence band goes downwards. If you apply forward bias, why? Because you are injecting extra electrons and extra holes into the same region. So the valence Fermi level. If you apply reverse bias, it goes the other way. Valence band goes up, conduction band goes down. So that's how quasi-Fermi levels split. What do I mean by all that? Fc minus Fv is roughly equal to Q times applied voltage on the diode. This is Shockley condition, split. Right? So as you split it, now we apply some, and I'm talking primarily of forward bias now, as you can see, because we are going to inject carriers and make it LED or make a LED or a laser, and then it starts floating up, floating down. Okay. Right. Now I can make a sketch of this condition when the Fc is here and Fv is here. You can take this Fc and value of Fv, plug it into the whole thing here, and when you plot the value, what you'll get is something like this. Let me just draw a dotted line here. You're going to get, so it will go start from -1. As you can see, this difference, the smallest value is -1 because both are zeros and ones, right? And the largest value is +1, right? And it goes through 0. And when you are under this situation, your curve will look something like this. Okay? So it will kind of go over to 1, +1. What am I plotting here? This is Fc of this Fv minus Fc. Does it make sense? I mean, essentially, this is dependent on how much carriers you're injecting. This curve is dependent on how much. And in this situation, when I have something like that, the total absorption coefficient is a product of alpha naught, which is this curve, and this whole quantity, which is this dashed line. It's the product of the two, right? Therefore, the total absorption coefficient now under this situation looks basically 0, 0, 0, and then it looks just like that. It's not very different. And you have kind of started, it's already started emitting light because NP is larger than Ni square already. And this is kind of already like a LED. But it's very weak right now. The emission is very weak. Yeah. What happens as you crank up the voltage? As you crank up the voltage, this moves even further here. It moves further down here. Increase the voltage. Because the splitting is Q times V, right? It increases. And so essentially you have more electrons now in the conduction band and more holes in the valence band. So, and the difference, Fc minus Fv, essentially what happens is this crossover point goes here. It starts shifting to the right as you inject more. Okay. And I think you can see very clearly that there is a very clear threshold, when this crossover point reaches the edge of the gap and goes above it, then something interesting is going to happen. Till then, basically you are kind of, so this process is, when you kind of are here or very close, then, it goes over like that, and you get kind of the highest, okay, so essentially this is the spontaneous emission process because NP has become larger than I squared, but the moment you cross this, and let's say your injection is such that your function looks like that. So now you have the product of a positive thing here and a -1 till here, and then it switches to +1. So basically the product is going to look like that. You see that? So because it's this times the negative part of it, then times 0 is always 0, so it gets pulled down and then it goes back up again to +1. So this is really the very important picture here. Basically, I hope you see what I did. I mean, essentially, by injecting more and more carriers, I reach a certain threshold of carrier density. And when does that threshold happen? That's when the Fc gets into the conduction band and the Fv gets into the valence band. Okay. All right. So what you have done really is made the semiconductor degenerate, and just to make it a little more clear, you have occupied all these states and you have unoccupied all these states. So this is the population inversion. Inverted the population, and that's what's shown here. Fill these conduction states with electrons and emptied out the valence band states, and that happens. I think you can kind of almost visually see it, that when Fc minus Fv becomes greater than equal to Ec minus Ev, which is the band edge or the Eg, and that's basically the photon energy. Okay, so when the photon energy is whatever transition you get out here, and okay, so when the bands enter this, I'll show a couple of slides later. You see that if you have actually let me just finish up this discussion now. So in this window, there's quite a bit of interesting things going on. So you have a little slice of energies here, depending upon the threshold. I mean, the amount of current you are injecting and all that, right? So this point will be determined by how much voltage and how much current you are injecting. So that's what determines it. But remember when I said you have to design the mode such that there is kind of one mode that falls, and which window should it fall in? It should fall in this window, because here your absorption coefficient is negative. And this is what is giving you gain, right? So in the laser cavity, you want the gain. Basically, the mode of laser that you want to design it with should be somewhere right in the middle, so that you select it out, that mode, and you get the most gain out. Does that make sense? If you are going to take this situation, or what have we done? We have basically taken a PN diode now with some quantum wells in the active region, and then we have built. Okay, so right now all we have done is we have injected a lot of current into it, applying a certain large voltage to split the Fermi levels, and then the light that's coming out is there is some amount of gain of the light that's coming out here. If you take this same semiconductor under this situation, so this region is in a very strange state, this region where the light is being generated, because now what you can do is, so this is current injection. What you can do is you can come in from the lateral edge, for example, and actually shine light, or you have another laser, a tunable laser, and you can see what happens as you kind of make a pass of light of different frequencies through this region, through the region where stuff has happened. You have changed the absorption coefficient. So all this has happened because of electrical injection. That's clear, right? You went from this absorption coefficient to this because of electrical injection. And now you are electrically injecting it still. You keep injecting DC, and then you come in with another light source and look at. And so what will happen is now the amount of light that goes in here will come out amplified here, right? Because this region has an absorption coefficient that's negative, right? If the energy is matched inside this window, right? If you go to this wavelength of light, or this energy of photons here, then this will pass through the material unhindered. There will be no absorption, no emission, right? Does it make sense? Because the absorption is 0. So this point would be optically transparent. So what you did is you took a semiconductor. If you had not applied the voltage and you pass a photon of this energy, it will get absorbed very fast because it's larger than the band gap, right? But now you turn this on, the voltage on, and this light will go through. So it's some sort of a switch in some sense. You can, by applying a voltage here, you let light go through or not go through. Right? So that's kind of an interesting aspect of this. And this is used in various, forms in electro-optical modulators, and some things like that. It's not just what I mentioned, but yeah. Okay, so. That's optically induced, so electrical injection induced transparency, gain, and interesting. Okay, so what I want to do is, I think I've told you the main basics of a laser, okay? And at least gone to a point where you can also start making plots of these things. Let me just, so I can maybe wait for a couple of minutes if there are any specific questions here, and then I'll go to the next topic, which is a couple of different kinds of lasers, interband, intersubband, some details of it, some design differences, and then kind of move to the next topic. Any questions? If not, okay, let me just explain one more thing. This is this momentum matrix element that I mentioned that goes into the the oscillator strength problem, and here what you typically are looking at. Don't worry too much about the details, but essentially the thing was there has to be some mismatch in the symmetry of the two bands or the two states that produce the light or absorb the light. And so if you have interband transitions, it has different bands that can emit light due to recombination have to be different by in a certain symmetry. So the general form of the absorption coefficient will be, again, this coefficient depending upon just the light and the bulk material properties times the matrix element squared, momentum matrix element squared, times the reduced density of states. The reduced density of states for 2D, which is the most popularly used semiconductor laser structure today, is quantum well based. So a 2D density of states, I think we have done that earlier. If you forget this LZ, this is the 2D density. This is effective mass divided by pi h bar square. Spin degeneracy of 2, value degeneracy of 1. Now, what it has, the way it's written here is you convert it to an effective 3D density of states by dividing by the width of the well, and that's the width of the well, LZ. So then it becomes effective 3D, has the same dimensions as what we had for the three-dimensional crystal. Okay? And then you're essentially the way it's written here is when you make the quantum well, you are going to now have absorption coefficient instead of the square root. It will look like this. The first state will be from, this is the quantum well, this is the ground state of the conduction band, this is the ground state of the valence band. So hole 1 and electron 1. Right? And the minimum energy for transition here is clearly from here to there. Right? So it's the band gap of the quantum well, the kind of bulk band gap of the quantum well plus this is the minimum energy. Right? The smallest energy photon that can be emitted from here. And then so that's where this edge occurs. Eg plus E quantum of electron, and it's written as minus hole. You understand what it is. The signs, you can fix it. And then so this transition, remember, this has basically one subband goes like that, another subband goes like that, and so you can have transition across the subband. Let me explain what I mean by that. Right. So ground state, and attached to the ground state is this EK diagram. Remember, we had kind of seen that, and attached to the. So in this plane, it can still move, right? Okay. And therefore, the transition primarily would be kind of from here to here, but there will be a little bit from here to there, a little bit less from here to there, depending upon the occupation. So that will give you the broadening of the emission from that state. And the density of states goes as basically just the DOS, and for a subband is the combined DOS. MR here is 1 over effective mass of this plus 1 over effective mass of that, right? Reduced mass. Okay. So what does it mean? The photon energy that's going to be emitted or absorbed must be larger than this quantity. And then by changing the quantum well width, you can change the edge here, right? Because you can shift the quantization energies, and then that's how you can. So if you inject carriers, typically what will happen is, the electrons, let's say you have an N side here, you inject electrons, you have P side here, inject holes, and you fill these states with electrons, fill those states with holes. And because you have not just one subband, you can have two subband, you can decide on the quantum well width and the height, which is the band offset, right? Depending upon your choice of compound semiconductor, you can fix those, right? If you have, for example, two subbands, two eigenvalues, two bound states. Then you inject electrons and holes. This is how remember the Fermi function is basically 1 far below, and then it goes to 0 gradually here. Does that make sense? And the density of states is constant, and so it was basically this is kind of the tail of the Fermi function, but suddenly there's a discrete jump because the second subband just kicked in, right? Therefore, Fermi function is still going down, but then DOS has suddenly doubled or something like that. So you have this little notch here. So the carrier density looks like that. Does that make sense, what we are sketching here? And similarly for the valence band. You see the valence band, so these are electron and hole densities in the conduction band here, hole density in the valence band. You see the valence band has much more holes. The reason for that is the valence band effective mass is typically much larger than the conduction band effective mass. You know, heavy holes and all. So you have this, and this particular mismatch is actually a bad thing for lasers, and people go to great lengths to, to make sure that it's not much of a mismatch. They are more symmetric, and I'll explain it why very briefly. So is that clear though? I mean, once you have carriers like this, this is what so the Fermi level of conduction band and valence band. Essentially, the whole thing just carries over to any quantized structure now. Wires, dots, whatever you have, it's the same. I mean, the idea is the same, right? So just the dot changes from one to another. That's all. Okay. So now so for example, you can now plot, instead of the band diagram, you can plot the gain as we were plotting. Now, what is the gain spectrum of a laser? It may seem fancy, but essentially all that it is this flipped upside down. That's the gain spectrum. As you can see, I mean, it's minus of alpha is gain, right? And so this is the plot. For a bulk material, it will basically look, for a bulk material, the gain spectra looks just, this curve here. That's the gain spectra. And for a quantum well, I think you know by now why. It's going to have maybe some steps like this, because you have DOS that's going like that, right? So, and this is the solid lines are calculated, and the dots are experimentally measured gain spectra for some infrared lasers, indium gallium arsenide quantum well lasers on indium phosphide. Remember this, you can lattice match for a certain composition of indium gallium arsenide with indium phosphide. So these are multi-quantum well heterostructure lasers. The quantum well width is 19 nanometer. These measurements are done at 19 Kelvin, these temperatures and all that. But you see this now, right? So the spectrum. The other very interesting thing is you notice one of them, the lower one here, for example, one of them is TE mode, the other is TM mode, transverse electric, transverse magnetic mode. And that has to do with, remember, the matrix elements I mentioned earlier. Those details I'm not going to ask you to bother about, but at least know where they came from. I mean, these matrix elements, cosine theta is basically the angle at which things are going out, and that determines whether a mode of light that is being emitted is TE or TM. So you can kind of fix that part of it. Okay? Is that clear? I mean, so this is the situation for, and you can see here, for example, for this gain spectra, the carrier density that is injected is of the order of about 2 times 10 to the power 12 per centimeter square. 2 times 10 to the power 12 per centimeter square. Electrons and holes in the quantum well, the sheet density. It's of the order of the charge you have in Hempt 2D channels. It's of the same order. Why? Because you know that when you have 2e times 10 to the power 12 per centimeter square, your Fermi level is now in the conduction band, right? So you know that, and or holes, if you have that many holes, it's in the valence band, so you get population inversion now. Does that make sense? Okay, so it's same order of magnitude. Typically for larger bandgap semiconductors, you need a little more. For nitrides, you need 5e12 or 1 times 10 to the power 13 per centimeter square, and so on. So it depends on the material. So this particular condition is called from the guys who wrote the first paper on it, at least Bernard Durfog, inversion condition, specific to semiconductors. But the aspect of the laser was figured out way earlier for masers and all that sort of thing. But specific to semiconductors, if you read these names, these are the guys who wrote the first paper that explain this is the condition you need for lasing in semiconductors. Okay, so what I'll try to now do is just go through a few slides. Sorry. Yeah, I'm going to skip a couple of things here. So the other thing is I didn't talk much about mirrors, but I think you realize that if I have, say, a quantum well like this is a very thick well. It's not even a quantum well. It's 200 nanometers of gallium arsenide, 2,000 angstroms. These used to be called the DH laser, the double heterostructure laser. There's no quantum well, but you have two heterostructures. You're injecting electrons from one side, and you're injecting holes from the other side. And the double heterostructure, what it does is it gives you a large band offset of conduction band here, which essentially doesn't let electrons to spill out into the n side, blocks them or reflects them. Similarly, for holes, you need a large valence band offset here, and you can reflect the holes. So if you have read Herb Kromer's this review article, you have seen nice pictures of why this is useful, because I think you realize now that you need to inject a certain amount of electrons and holes, a certain threshold, to create lasing. But if you don't kind of confine the electrons and holes, they will spill over, and you won't get that threshold at all. So the double heterostructure really lowered the threshold for lasing by huge amounts. The other very big advantage of the double heterostructure laser is, as we had talked about earlier, if you have a small band gap region, it has a larger refractive index, right? It has a larger refractive index. So this is a refractive index plot now. But light wants to be in regions of lower refractive index. Basically, from Maxwell's equations, I think you know that energy of light goes as half E squared, right? Epsilon E squared. And you can do the math here. Essentially, you will find that if you have two regions of different dielectric constants, the intensity is maximized in the region of lower refractive index. But you see there's kind of a very interesting trade-off, because the light is being generated right here, right, in this region. And there are a lot of carriers here. And what you typically, one of the very big loss mechanisms is what's called free carrier absorption. If you have too many free carriers, they can absorb. These are, higher order. It get kicked up to higher places in the bands and all that. And you want to avoid that. So you want basically the light tail to be very high outside, not inside here. So that's the design typically people use. And I'm going to actually just look at a few designs of this first, and then So what you want is the electrons and holes to be confined within the quantum well, but you want light to be spread out, not confined in the quantum well region. So what people now do, there are many kinds of designs. Here's the quantum well. Then you go to a slightly larger band gap region, and then you go to even wider band gap region, and you start shaping. This is the electron distribution or carrier distribution. This is the photon mode distribution, light distribution. You want it to be. So essentially, what you want to do is kind of, if you take the product of the two, you want to maximize that. You want to be, you want to minimize that. The light should be farther out. So you want to kind of lower because of you want to avoid free carrier absorption. So. Now, one of the other details I wanted to mention, let's see, we have about 15 minutes or so. So that's just the aspect of light emission, and then essentially the light will now be guided if you have this sort of a structure. If you have this sort of a structure where you have a refractive index difference, and light is generated here, and if you plot the intensity of light, it's kind of looking something like that, right? And the light, essentially it will be something like that, and it will be what is it? It's basically it's guided this way. It wants to kind of get out that way. That's the intensity. Not much vertically. For example, in this particular picture, you can change it depending upon the refractive indices and such. But so the intensity of light kind of starts looking like that. And what you can do now is you have now the option of making a laser in two ways. One of them is you take this LED structure, and then what you do is you kind of cleave the crystal along two directions here and expose a very almost atomically smooth facet. Cleave it, make it almost atomically smooth, and that's a mirror. So essentially what I'm trying to say is this is a p-n junction now injecting carriers, and then this face and the other face on the other side. These are the two mirrors. You just cleaved it. This is the cheapest way of doing it, and then essentially those are the two mirrors, and the light this mode kind of bounces back and forth in between these two, and that's your gain medium now. So the cleave facets, this is called an edge emitting laser because the light is going to come out from the edge of the wafer. So it's the edge emitting laser, and then it is going to come out along the sides, so as you can see, the quantum well emitter. So all the details inside. Let me just give you a rough, rule of thumb. What is the reflectivity of an edge emitting cleaved edge? It's actually rather low. It's like 0.3, 30% reflectivity. Okay. So there's quite a bit of light leakage in these structures, but I think that even after all this, the net efficiency can be very good. I mean, so because the material quality can be improved, the loss can be lowered, and all that kind of stuff. So there, for a cleaved edge. The other way is if you want light to come out vertically rather than from the edges. And that would be called a vertical cavity surface emitting laser, or VCSEL, VCSEL, right? Vertical cavity. And I think it's very clear what you need to do there is to put the mirrors on top and bottom and bounce the light back and forth like this, right? And the way that you do that is basically the mirror here is basically a periodic grating of semiconductors of different refractive indices. I think you know that if you have a periodic grating of something, if your light is going through and the Maxwell equation sees the refractive index is changing periodically, right? It will gap it, and basically you create a gap for that mode. Just like electrons is going through a crystal, and you see a periodic grating of atoms, you have a band gap now, right? That's what happens whenever you add periodicity. So essentially, as you change the refractive index in this direction, even with a small value, you just kind of grow. These are typically would be called a superlattice of Al gas, for example. Al gas, larger band gap, smaller refractive index, gas, smaller band gap, larger refractive index. So basically, if your NZ plus L is refractive index becomes periodic, then you can actually do the numbers. You can calculate what would be the reflectivity of this sort of a distribution. So this would be called a DBR, or a distributed Bragg reflector. And typically with a few tens of periods, you can get reflectivity in a DBR close to 99.99%. So but the challenge typically is you have to grow relatively thick, and if you have strain and all that, you've got to figure out the right materials now, right? So that's typically the challenge here. And if there is not much strain difference, then you also need to maximize the refractive index mismatch. These two parameters essentially give you the, and it's absolutely critical, as you can see very clearly, that the DBR band gap should be much larger than the photon that's going to come out. Otherwise, it'll get reabsorbed. That's a bad idea. So it should be optically transparent, right? So you can get 99.9% or so reflection in DBRs. And these are basically, this is a much simpler epitaxial growth because you have basically, 3 or 4 quantum wells. It's kind of a LED structure with some tweaks. There's some tweaks, obviously, but whereas this is a much longer growth. You have all the DBRs and all that stuff. Yeah. Okay, so some other small design, evolution. This is, by the way, some of the design aspects of it from Weissbuch and Winter's book, and you can read it actually if you understand the basic idea. It should all kind of make sense. I think this part I was starting a quick summary and then some design details. This we understand. If you have a bulk material, the gain spectrum is going to look like this, right? We discussed that today. If you have a quantum well, it's going to look something like that, an abrupt edge, right? Actually, if you go to quantum wires and dots, it will have more sharper features because of the density of states. Basically, the gain spectra, the beginning of the gain spectra, left edge is a picture of the density of states, really, right? So, yeah. Now, the single quantum well, I think you can see that the density of states will essentially have 2 steps. For example, if you have two subbands, and then when you merge into the bulk, it becomes square root again. Is that clear? I mean, that's the total density of states, right? Including also the bulk states. If you have multiple quantum wells, again, depending upon states, you are now starting to shape the gain spectra of the material based on what structures you're using. And now this is a very nice structure where you have what's called a graded index separate confinement heterostructure, GRINCH, graded index separate confinement heterostructure. Why is it called that way? It's basically you have a quantum well, but you now compositionally grade the material from, say, gas to about 30% al gas outside or something like that, or in GaN to GaN or something. Compositionally, continuously graded, not abrupt. And so what that does is so your electronic states look like that, and electronic cavity look like that. Essentially, what it really does, the biggest thing about the Grinch is it lets you design the optical confinement very nicely. The grading, because your refractive index is, you're continuously changing it, and it helps you again separate the photon, the photonic. I think it's probably in the next slide or some. Let me check. Maybe I have not put it here. So all these graded index or separate. This is called a separate confinement heterostructure quantum well. This is also there in Rocket's book, which I had shown earlier. This is the SCH, or the separate confinement heterostructure. And if you kind of, this region, if you grade it, that's called the GRINS, graded index, separate confinement heterostructure. These are just various kinds of, and you can read why exactly one is good or the other is bad. So, here, for example, in the graded index, what you do is you cut down the amount of electrons in this region, because all of them are funneled down here. Therefore, the light that is localized here and here doesn't see too many free carriers. Whereas in the separate confinement, it sees a bunch of free carriers. It's quite a bit more. So you kind of reduce the free carrier loss by grading it. And you start getting into all these design details now. The other very important design improvement in lasers was from his idea from Ilya Yablonovich back when he was in Bell Labs. Very interesting idea. Remember I mentioned that if your density of states is mismatched, if your conduction band density of states, basically conduction band effective mass is typically much smaller than the valence band effective mass, and 2D, the height, is basically the effective mass, right? So conduction band DOS is like this, but valence band DOS is like that. Right? But if you make a p-n junction, you're going to inject electrons and holes. You are injecting exactly equal number of electrons as holes. Right? N is equal to P inside. I mean, the injection into the quantum well is pretty much exactly the same into the holes and electrons. As a result, the areas under these two shaded regions are the same. N and P are the same. And I think you can see, even looking at this, that because the conduction band DOS is small, the Fermi level of the conduction band is going to climb up very high. Right? Whereas the valence band will not climb very high because the DOS is so large. It will be stuck over here. Does that make sense? Because the DOS is high. But and the EF and E, these FC and FV have to adjust to populate the two bands with the number of carriers you've injected. They'll be wherever they need to be to ensure that you have the right carriers there. And you see now this is a problem because this is not going to lase. Right? You have not achieved population inversion here, right? In some sense. I mean, well, you have but you have not, actually, no, that's correct what I said. You have not met the Bernard-Durfog inversion condition. Basically, this should be inside here and this should be inside here, but you have not achieved it. Okay. So therefore, this is a little harder to lase, and you have to. So these lasers will have very high thresholds for lasing. You have to inject a lot more carriers, and then kind of start maxing out this thing here, and then by that time this will be way too high, and things like that. So it's mismatched. Right? So what was proposed, and this is called a strain quantum well laser. By applying strain in the quantum well, growing it on lattice mismatched substrates. Remember, if you grow, let's say, I think we know if you choose different lattice constants, you can strain the material, and when you apply strain, you can rearrange the valence bands. You can push up some bands and push down some other bands. And when you push up, typically the light hole or the split off to the top, that becomes very similar to the conduction band. It becomes very symmetric. And then that lowers the threshold injection. I think you can pretty clearly see now why it will lower it, right? With much lower hole density, you can start pushing the Fermi level into the valence band now. Does that make sense? And achieve inversion condition. So that's one of the advances in strain quantum well lasers, and they are also obviously very useful, and they're used today in telecom sort of wavelengths, and then being looked at carefully also for visible and such. This picture is not very clear, but essentially I think what you can see is if you reduce the density of states, go from quantum wells to quantum wires to quantum dots, your dots really get sharper, right? It goes higher and higher. Again, from a very simple sort of paper, calculation, and this is described in Weisswig-Winter. Sorry for this picture, but essentially what's showing here is the gain for lasing gain with threshold current, and here's a bulk material, here's a double heterostructure, here's quantum wells, here's quantum dots. That's what it's showing. So you can get into lasing at a lower and lower threshold threshold injection current. That's what's showing as you go to lower dimensions. Obviously, you have to play the game right. You can have like one quantum dot with a very low lasing threshold, but there's almost no light coming out, right? I mean, you need to play the game right. You have to have enough light emitters as well. You have to have high intensity as well, not just a low threshold, right? So here's again alpha rho. By the way, this is also from an article that's posted on the web. Threshold current of lasers over the last things have improved since 2000, but you can see that it used to be bulk material and then double heterostructure with thick quantum wells, then very thin quantum wells with all this separate confinement and all this. This is a short period superlattice SPSL. I mean, all these heterostructure designs went from 10 to the 5 to 10 to the 3 to 10 to the 2. With quantum dots, you are talking about 10 amp per centimeter square. It's very, very low threshold now. The ultra low threshold lasers this is for infrared long wavelength lasers. So 10 amp per centimeter square is kind of in the LEDs region. You can, basically this is very low, extremely low threshold and very high efficiency now. So that's kind of nice improvement. One of the issues with quantum dot lasers is it's very hard typically when you grow to have all the quantum dots the same size because they are grown. We will talk about growth starting Thursday, actually structure and growth and all that starting Thursday. So today is the last class of electronic or photonic properties. So, but we'll see that it's because they are typically what the dots that are used for lasers are self-assembled. You don't predefine the sizes. So there's always a broadening in the size distribution, and that's one of the challenges in making very good quantum dot lasers and such. Okay, so this is not as sharp. There's some broadening because of size distribution. Okay, so one of the things which is very interesting, so this is for infrared. Typically lasers would be of the order of kiloamp per centimeter square, but I think as you see, you can now get at room temperature 10 amp per centimeter square, very low wavelength. For visible wavelengths, I think this is a nice picture that I borrowed from Nakamura's article. So this is visible now, and this is in the blue. This is an output external quantum efficiency, meaning everything inclusive. What's in in the voltage times current, and this is the amount of photons out in watts out, light in the light. So in a LED, typically what happens is because at very low current densities, typically tens of about 100 amp per centimeter square, and you push it further, and then it starts decaying pretty sharply for LEDs. Whereas lasers get better at high carrier injection, and I think because you need inversion and all that. So there's also a lot of discussion now of by the way, look at the numbers. These are 70% light conversion efficiency. It's huge. I mean, it's really, really amazing. Light bulb is 4% or so. Okay, so just for comparison. So the laser obviously has directionality, so that's another very nice thing. Nice thing or not, but I think well, this is people are starting to replace the headlights of cars using lasers now. BMW and Audi, they're starting, so this is a laser light, and obviously the initial introduction is not what it does is in a LED you are getting a certain amount of watts per centimeter square. In a laser, because you are at a current density about 10 times higher, your area of the chip can be 10 times lower. It's a very small area, and it's giving out the same amount of light with the same efficiency, right? So you suddenly shrink everything, and then the other beauty, obviously, of the laser is it is directional. Right? So you can steer your beam, you can turn off the beam for some people. I mean, if there's a car in front of you, you don't want them to get high brightness, but you want the rest to be bright, and they are doing that now. I mean, with slight electronic control inside it, you kind of have specific regions of lighting rather than all regions of lighting. So and the other very cool thing is these devices, these photonic devices based on compound semiconductors, are designed at the quantum mechanical level to emit light, right? And that what we understand. You can take it and you can switch it on and off, or you can modulate the light at close to 100 megabits or almost a gigabit per second. You can have the light on all the time, but you have a little modulation, and that can also use to transmit data. And then that's another very new. For LEDs, that's called Li-Fi, light fidelity instead of Wi-Fi, and it's being looked at interesting. And also for lasers, obviously. I mean, lasers are used to transmit data today, and so these are all the new innovations that are happening. And you can't do this with a light bulb. That's difficult because that emits heat by thermal aspect, and thermal lifetimes are very milliseconds or slower. You can't get data out that fast. Okay, so I think it took a little longer time today, but I'll end this stuff today, and then next class we will. So I've finished basically about 4 or 5 chapters. I forget of. Please read chapter 3 in detail for Rocket and Weissbook Printer. I post the slides here, and the next topic would be chapters 4 and 6. So start with chapter 4 on Thursday, okay, which is we look at structure of the compound semiconductors and such. So about homework and assignments. An exam. What I'm going to do is, the reason I haven't posted is I want to actually merge the third assignment with 1 or 2 problems in the end, which will be your midterm. So it will be a take-home. You do it. It will be a little bit more of a design problem, which will be open to you again, and you'll have enough time to solve it, okay, for the midterm. Okay, good.